At the dawn of the jet age, pressurization was sold as a miracle of modern engineering. A fragile human body could be carried to altitudes where the outside air could not sustain life, sealed inside a metal shell that promised safety, comfort, and absolute control over the environment. The fuselage skin was presented as a triumph of materials science, thin enough to save weight, strong enough to contain a pressure differential of several pounds per square inch, repeated tens of thousands of times. Each rivet, each lap joint, each frame ring was calculated to work in harmony, distributing loads so precisely that failure seemed mathematically impossible. In design offices, the aircraft was not just a machine. It was an argument that human ingenuity had finally mastered the hostile physics of the upper atmosphere. The cabin would be inflated like a lung, gently, predictably, on every climb. And on every descent, it would relax again, obediently returning to ambient pressure. Confidence was built into every drawing. What those drawings concealed was the brutal reality of cyclic stress. Pressurization is not a static load. It is a relentless pulse. With each flight, the fuselage skin is forced outward, microscopically stretching as the internal pressure exceeds the thin air outside. This hoop stress concentrates around cutouts, doors, cargo hatches, antenna penetrations, and most critically, windows. Engineers understood the equations. They calculated average stresses, applied safety factors, and trusted that aluminum alloys, riveted together with care, would endure. But they underestimated one thing: geometry. Sharp corners, overlapping joints, and rivet holes act as stress amplifiers. At these points, the local stress can be several times higher than the value predicted by simple models. In the quiet confidence of the design phase, these concentrations were accepted as tolerable. After all, no single pressurization cycle came close to the ultimate strength of the material. Inside the metal, however, physics was keeping its own ledger. Aluminum alloys, like all structural metals, are vulnerable to fatigue. When subjected to repeated loading and unloading, even stresses far below the yield strength can initiate microscopic cracks. At first, these cracks are invisible, confined to the crystalline lattice around a rivet hole or the edge of a cutout. Each pressurization cycle becomes a tiny hammer blow, driving the crack forward by fractions of a millimeter. Thermal expansion compounds the problem. On the ground, the fuselage cools. At altitude, it chills further. During descent and turnaround, it warms again. These temperature changes cause the metal to expand and contract, adding another oscillation to the stress field. None of this is dramatic. None of it triggers alarms. The aircraft continues to fly, cycle after cycle, accumulating damage in silence. The danger of pressurization failure lies in this invisibility. The cockpit instruments show cabin altitude within limits. The passengers feel nothing unusual. Maintenance inspections, often visual, reveal no obvious defects. The crack grows beneath layers of paint and sealant, shielded from casual detection. Engineers call this crack propagation, and it is governed by fracture mechanics, not simple strength calculations. Once a crack reaches a critical length, the remaining intact material can no longer redistribute the load. The structure transitions from stable to unstable in an instant. What has taken thousands of flights to develop can reach catastrophic failure in less than a second. When that moment arrives, the physics is unforgiving. Cabin pressure seeks equilibrium with the outside environment. If the fuselage skin ruptures, the pressurized air inside the cabin accelerates toward the opening, tearing at the structure with explosive force. This is not an explosion in the chemical sense, but the effect is just as violent. The rapid decompression produces a shock wave that can rip panels loose, collapse floors, and impose enormous transient loads on the airframe. The failure often propagates along structural seams, following the path of least resistance, unzipping sections of the fuselage skin. In extreme cases, large portions of the aircraft can be torn away, exposing the interior to the open sky. The immediate aftermath depends on altitude, aircraft speed, and the extent of the rupture. At cruising altitude, oxygen levels drop instantly. Crew and passengers have seconds to react. Structural damage can compromise control systems routed through the fuselage, affecting flight surfaces far from the initial breach. Even if the aircraft remains controllable, the shock to the system is profound. Crews are trained for decompression, but no training fully prepares them for the violence of a structural failure driven by pressurization. The machine that moments ago felt solid and predictable suddenly reveals how thin the margin of safety truly is. When the wreckage is examined, or when a damaged aircraft is brought back to the hangar, the investigation begins with a microscope, not a blueprint. Forensic engineers strip away paint, cut sections from the fuselage, and trace the origin of the fracture. They look for telltale signs, beach marks indicating progressive fatigue, corrosion pits that served as crack initiators, rivet holes elongated by cyclic loading. Often, the root cause is not a single mistake, but a chain of assumptions. A window corner shaped for manufacturing convenience. A lap joint designed to save weight. A testing regime that validated static strength but failed to simulate realistic pressurization cycles over the aircraft's intended service life. The arrogance is subtle, embedded in the belief that existing knowledge was sufficient. From these failures emerged a new discipline. Full-scale fatigue testing became mandatory, with fuselages cycled thousands of times in test rigs that simulate years of service before an aircraft ever carries passengers. Window geometries were redesigned with rounded corners to reduce stress concentration. Materials science advanced, producing alloys with better crack resistance and predictable fracture behavior. Inspection techniques evolved from visual checks to non-destructive testing methods capable of detecting cracks before they reached critical length. The industry learned, painfully, that pressurization is not merely a comfort feature. It is a structural load case as severe and consequential as aerodynamic lift. The legacy of pressurization failures is written into every modern airliner. Redundant load paths, damage-tolerant design philosophies, and conservative certification standards are direct responses to lessons learned when microscopic cracks were allowed to grow unchecked. Each flight today is safer because of machines that failed in the past, not despite them. The fuselage remains thin, the pressure differential remains immense, and the physics remains unchanged. What has changed is the humility with which engineers now approach the problem. The history of aviation is written with steel, ingenuity, and the will to challenge limits. It is also written with fractures, fatigue, and the consequences of believing a structure is invincible. Welcome to the vault. Pressurization did not merely reshape passenger comfort. It redefined the fuselage as a pressure vessel. In early design philosophy, the aircraft body was treated primarily as a beam, carrying bending loads from lift and weight. Pressurization introduced a second identity. Now the fuselage had to behave like a thin-walled cylinder, resisting internal pressure that acted uniformly, relentlessly, across every square inch of skin. This dual role created a structural paradox. To be efficient, the skin had to be thin. To be safe, it had to endure cyclic stress without accumulating irreversible damage. Engineers relied on classical elasticity theory, assuming that as long as stresses remained below yield limits, the structure would endure indefinitely. That assumption was mathematically elegant and catastrophically incomplete. The physics of pressurization is deceptively simple. At cruising altitude, outside pressure may be less than a quarter of sea-level atmospheric pressure. Inside the cabin, pressure is artificially maintained at a level equivalent to several thousand feet above sea level. The difference between these two environments produces a pressure differential typically between 7 and 9 psi. That number appears trivial, but multiplied over the surface area of a wide-body fuselage, it translates into millions of pounds of outward force. Every frame ring resists expansion. Every stringer carries tensile load. Every rivet becomes a critical transfer point between components. The system functions only because the loads are distributed with near-perfect symmetry. Any deviation, any geometric irregularity, disturbs that balance. Cutouts are the unavoidable enemies of pressurization. Windows, doors, and access panels interrupt the smooth flow of stress through the fuselage skin. At these locations, load paths must bend around voids, concentrating stress at edges and corners. Early jet designs favored rectangular or near-rectangular windows to maximize visibility and simplify manufacturing. On paper, the additional stress was accounted for with increased material thickness or reinforcement. In reality, the sharp corners of these windows acted as crack starters. Stress concentration factors at these corners could be several times higher than in surrounding skin. Under cyclic pressurization, these points became laboratories of fatigue. Fatigue does not announce itself. Unlike overload failure, where material tears dramatically once limits are exceeded, fatigue is quiet and patient. It begins at the microscopic level, where dislocations form within the metal's crystalline structure. At a rivet hole or sharp corner, these dislocations accumulate, forming microcracks measured in microns. Each pressurization cycle opens the crack slightly. Each depressurization allows it to close, rubbing the crack faces together and sharpening the tip. This process reduces the energy required for further growth. Over time, the crack accelerates, transitioning from slow, stable propagation to rapid, unstable fracture once a critical length is reached. Thermal cycling adds another layer of complexity. Aircraft fuselages experience wide temperature gradients. At altitude, skin temperatures can plunge far below freezing. On the ground, solar heating and ambient conditions warm the structure unevenly. Aluminum alloys expand and contract with temperature changes, inducing additional stresses that superimpose on pressurization loads. Riveted joints, composed of dissimilar materials and varying thicknesses, respond differently to these changes. Differential expansion creates localized shear and tension, further aggravating fatigue initiation sites. None of this is visible from the cabin. None of it affects short-term performance. But structurally, the clock is always running. Maintenance culture initially lagged behind this reality. Inspection intervals were based on flight hours and calendar time, not pressurization cycles. Visual inspections focused on obvious damage, corrosion, or deformation. Fatigue cracks, buried beneath paint and sealant, often went unnoticed. Non-destructive testing methods existed, but their application was limited by cost, accessibility, and the belief that catastrophic fatigue failure was unlikely if design stresses were conservative. This belief was reinforced by early success. Aircraft accumulated thousands of hours without incident, reinforcing confidence in the original assumptions. The moment of failure, when it comes, is dictated by fracture mechanics, not pilot input. Once a crack reaches critical length, the remaining intact material can no longer sustain the applied stress. The cracked tip accelerates at near-sonic speed through the metal, guided by stress fields and structural geometry. Pressurized air rushing through the opening amplifies the failure, imposing dynamic loads far greater than those seen in steady-state conditions. The fuselage skin may tear longitudinally, following rivet lines or lap joints. Frames can buckle. Floors can collapse as pressure equalizes between compartments not designed for sudden differential loads. The violence of decompression is often misunderstood. It is not simply air escaping. It is stored elastic energy being released. The fuselage, stretched outward under pressure, snaps back as the load disappears. This rebound can be as destructive as the initial rupture, bending frames inward and propagating damage beyond the original failure site. Loose objects become projectiles. Structural members designed for gradual load changes are suddenly subjected to impulses lasting milliseconds. In extreme cases, the aircraft's aerodynamic integrity is compromised, altering lift distribution and control response at the worst possible moment. Survivability depends on redundancy and luck. Modern designs route critical systems away from known failure paths, but earlier aircraft often concentrated wiring, control cables, and hydraulic lines along the fuselage crown or floor. A tearing skin could sever multiple systems simultaneously. Even when control is retained, the crew must contend with hypoxia, noise levels exceeding human tolerance, and rapidly changing aircraft behavior. Training emphasizes oxygen masks and emergency descent, but structural damage introduces variables that no checklist can fully address. When investigators examine such events, they reconstruct the failure backward in time. Fracture surfaces are studied under scanning electron microscopes. The presence of fatigue striations reveals the incremental growth of the crack. The spacing of these striations can even indicate the rate of propagation per cycle. Corrosion products may point to environmental contributions. Manufacturing records are reviewed to identify deviations, improperly drilled holes, oversized fasteners, residual stresses introduced during assembly. The investigation often reveals that no single error caused the failure. Instead, it was the cumulative effect of design decisions, operational realities, and maintenance limitations interacting over years. The concept of damage tolerance emerged from these lessons. Rather than assuming a structure would remain crack-free, engineers began designing for the presence of flaws. The question shifted from, will a crack form, to how long can the structure safely operate with a crack before it becomes critical. This required conservative assumptions, robust inspection regimes, and fail-safe features that prevent a single crack from leading to total structural collapse. Lap joints were redesigned to avoid hidden crack growth. Tier straps and crack stoppers were introduced to arrest propagation. Window shapes became rounded, distributing stress more evenly and reducing concentration factors. Certification standards evolved accordingly. Full-scale pressurization tests subjected fuselages to tens of thousands of cycles, often beyond their intended service life, to observe where and how cracks developed. These tests were not symbolic. They were destructive by design, intended to force failures in controlled environments rather than in revenue service. Regulators demanded proof that cracks could be detected and managed before reaching critical size. The industry, chastened by experience, accepted these requirements as necessary costs of safety. Pressurization failures exposed a fundamental truth of aerospace engineering. Strength is not durability. A structure can be strong enough to withstand extreme loads once, yet fail under modest loads applied repeatedly. The arrogance lay in equating the two. Early designers trusted static margins and underestimated time. The metal did not forget those cycles. It recorded each one, silently, until the sum became unbearable. In modern aircraft, the lessons are embedded everywhere, from material selection to structural layout to inspection philosophy. Composite materials, while resistant to classic metal fatigue, introduce their own challenges, such as delamination under cyclic loading and impact damage. Pressurization remains a critical load case, now analyzed with computational tools that model crack initiation and growth with remarkable precision. Yet the underlying physics has not changed. Pressure still seeks equilibrium. Materials still age. Geometry still matters. Every pressurized flight is a negotiation between human ambition and physical law. The cabin feels serene, isolated from the chaos outside, but the fuselage skin is always working, stretching and relaxing, cycle after cycle. It is a reminder that aviation safety is not achieved by eliminating failure, but by understanding it deeply enough to stay ahead of it. The most dangerous aspect of pressurization failure is not the rupture itself, but the long period of false normality that precedes it. Aircraft age quietly. Their outward appearance changes little over years of service, while internally the structure evolves under repeated stress. Each pressurization cycle adds another data point to the material's history, another increment of damage stored in the lattice of the metal. Engineers describe this as cumulative fatigue damage, but that phrase fails to capture the reality. This is not simple wear. It is a progressive weakening that follows precise physical laws, indifferent to schedules, maintenance budgets, or confidence born from past success. At the microscopic level, fatigue begins where stress is highest and material continuity is weakest. Rivet holes are prime candidates. Drilling introduces local plastic deformation and residual stresses. Even when executed perfectly, the process disrupts the uniform grain structure of the metal. Under cyclic loading, these disturbed regions experience slip along crystallographic planes. Over thousands of cycles, persistent slip bands form, eventually opening into microcracks. These cracks are initially so small that they do not significantly affect load-bearing capability. The surrounding material easily redistributes stress, masking the defect entirely. As the crack grows, however, the stress field around its tip intensifies. Fracture mechanics describes this with the stress intensity factor, a parameter that increases with crack length and applied load. While the overall fuselage stress remains unchanged, the local stress at the crack tip rises inexorably. This is the essence of invisible degradation. A structure can appear unchanged while its true margin of safety erodes steadily. The crack does not grow linearly. Early growth is slow, almost negligible. But as length increases, Each subsequent cycle advances the crack further than the last. The process accelerates quietly, crossing thresholds that were never anticipated in original design calculations. Environmental factors often accelerate this progression. Moisture trapped in lap joints promotes corrosion, particularly in aluminum alloys susceptible to pitting. Corrosion pits serve as additional stress razors, reducing the effective cross-sectional area and creating new initiation sites. Chemical reactions at the crack tip can weaken atomic bonds, a phenomenon known as corrosion-assisted fatigue. The result is a synergistic effect. Pressurization cycles drive crack growth, while the environment lowers the resistance of the material. In such cases, inspection becomes even more difficult, as corrosion products can obscure cracks or be mistaken for superficial damage. Operational realities further complicate the picture. Aircraft rarely fly identical profiles. Short-haul operations subject fuselages to more pressurization cycles in a given calendar period than long-haul flights. Rapid turnarounds reduce time for thermal equilibration, increasing temperature gradients and associated stresses. Minor ground damage, such as impacts from service equipment, can introduce additional flaws that interact with existing fatigue cracks. None of these factors were fully appreciated in early pressurized aircraft programs, where service lives were estimated conservatively but without comprehensive fatigue data. The progression toward failure often passes unnoticed even as warning signs emerge. Small cracks may cause subtle changes in cabin pressurization behavior, such as slightly increased leakage rates. These symptoms are easily attributed to seals or valves rather than structural integrity. Maintenance actions focus on restoring system performance, not investigating the deeper cause. In this way, the structure communicates distress signals that are misinterpreted or ignored. The aircraft continues to operate, its apparent reliability reinforcing the belief that the design is sound. When the crack reaches a critical size, the nature of the problem changes abruptly. The remaining intact ligament of material can no longer sustain the applied load. At this point, the structure transitions from damage tolerance to instability. The crack tip accelerates dramatically, driven by the stored elastic energy in the pressurized fuselage. This transition is governed by fracture toughness, a material property that defines resistance to crack propagation. Once exceeded, no amount of redundancy or pilot skill can arrest the failure. The sequence of catastrophic decompression unfolds faster than human perception. In milliseconds, the crack races along stress paths defined by geometry and construction. Rivet lines, lap joints, and stringer attachments guide the tear, creating characteristic failure patterns. Pressurized air escaping through the rupture generates aerodynamic forces that peel back skin panels, widening the opening. The sudden loss of pressure produces a powerful outflow that can dislodge interior components and impose upward loads on floors designed primarily for downward passenger weight. The structure experiences load cases never envisioned in certification analyses. Simultaneously, the aircraft's aerodynamics change. A breach in the fuselage alters airflow, introducing turbulence and asymmetric forces. If structural members associated with control systems are damaged, the crew may lose authority over certain flight surfaces. Even in cases where control remains intact, the noise and vibration inside the cockpit can be overwhelming, complicating communication and decision-making. Hypoxia becomes an immediate threat, reducing cognitive function within seconds at high altitude. The margin for error narrows to almost nothing. From an engineering perspective, the most sobering realization is that none of this violates physical law. Every step of the failure sequence follows directly from known principles of mechanics, thermodynamics, and materials science. The tragedy lies in the gap between theoretical understanding and practical application. Early engineers knew that fatigue existed. They knew that stress concentrations mattered. What they lacked was empirical evidence of how these factors interacted under real operational conditions over long periods. In some cases, they also lacked the institutional humility to question optimistic assumptions. Post-event investigations often reveal that the critical crack had been present for many flights before failure. In hindsight, it seems obvious that the structure was living on borrowed time. But hindsight is unforgiving. At the time, the absence of prior incidents was interpreted as proof of safety rather than as a warning that the system was accumulating risk invisibly. This is the core danger of pressurization-related fatigue. It rewards complacency until it suddenly punishes it. The response to such failures reshaped not only design practices, but also organizational culture. Airlines and manufacturers began to recognize that safety margins erode silently and that absence of failure is not evidence of robustness. Structural health monitoring became a priority. Inspection intervals were recalibrated based on cycles rather than hours. Non-destructive testing techniques, such as eddy current inspection and ultrasonic scanning, were refined to detect subsurface cracks before they reached critical length. Training emphasized the interpretation of subtle signs that might indicate deeper structural issues. Engineers also revisited assumptions about load paths. Redundancy was redefined not just as multiple components performing the same function, but as multiple independent load paths capable of carrying pressure loads even in the presence of damage. This led to multi-layered skin concepts, bonded structures with crack-arresting features, and design philosophies that assume cracks will form and grow. The goal shifted from preventing cracks entirely to managing them predictably. Yet, even with these advances, pressurization remains a fundamental vulnerability. The physics cannot be redesigned away. Every cycle still contributes to fatigue. Every cutout still concentrates stress. The difference today lies in awareness and mitigation. Modern computational tools allow engineers to model crack initiation and growth with remarkable fidelity, but these models rely on accurate input and conservative assumptions. Overconfidence remains a latent risk. The history of pressurization failures serves as a reminder that complexity breeds uncertainty, and uncertainty demands respect. The invisible degradation of a pressurized fuselage is a slow negotiation between material limits and operational demands. It unfolds quietly, without drama, until the final moment when accumulated damage manifests with sudden violence. This duality is what makes pressurization failures uniquely unsettling. They reveal that the most dangerous threats are not always dramatic or obvious. Sometimes, they are hidden in plain sight, encoded in the very success of a design that appears to work perfectly until it doesn't. The transition from latent damage to catastrophic failure is not gradual. It is instantaneous, governed by thresholds that, once crossed, offer no warning and no recovery. In the context of a pressurized fuselage, this moment represents the sudden release of years of accumulated stress. The aircraft does not fail because it is weak in that instant. It fails because it has been quietly weakened over thousands of prior cycles. When the structure finally yields, the physics unfold with brutal efficiency. At the critical moment, the crack that has been growing invisibly reaches a length at which the remaining intact material can no longer sustain the applied hoop stress. The stress intensity factor at the crack tip exceeds the fracture toughness of the alloy. This is the point of instability. The crack accelerates from millimeters per cycle to meters per millisecond. The fuselage skin tears open along paths dictated by geometry, rivet patterns, and residual stresses locked into the structure since manufacture. What had been a sealed pressure vessel becomes, in an instant, a conduit for explosive decompression. The pressurized air inside the cabin escapes violently through the breach, driven by the pressure differential between the interior and the thin atmosphere outside. This outflow is not uniform. It forms a high-velocity jet, exerting aerodynamic forces on the edges of the rupture that can exceed the loads experienced during normal flight. Skin panels are peeled back, lap joints unzip. Frames and stringers, designed to share steady loads, are suddenly subjected to concentrated forces far beyond their design envelope. The fuselage, once a smooth cylinder, begins to deform asymmetrically under the combined effects of pressure loss and external airflow. The decompression itself propagates structural damage. As the internal pressure drops, the fuselage skin rebounds inward, releasing stored elastic energy. This snapback effect imposes additional bending and shear loads on frames and floors. In aircraft with multi-compartment cabins, pressure differentials develop between sections, driving air through interior openings with hurricane force. Floors, often designed as non-pressurized elements, can fail under upward loads, collapsing and severing systems routed beneath them. Control cables, electrical wiring, and hydraulic lines are vulnerable in this chaos, their failure compounding the emergency. Aerodynamically, the aircraft is thrown into a new regime. The sudden breach alters airflow around the fuselage, creating turbulence and asymmetric drag. If the rupture is near the wing root or tail, the disturbance can interfere with lift and stability. At high speeds, the external airflow interacting with the opening can induce flutter-like oscillations in surrounding structure, further accelerating damage. The aircraft's response becomes unpredictable, shaped by the location and extent of the failure rather than by pilot command. Inside the cockpit, the sensory assault is immediate and overwhelming. The noise of decompression can exceed 140 decibels, rendering verbal communication nearly impossible. Loose objects are violently drawn toward the breach. Oxygen levels plummet, and without supplemental oxygen, consciousness can be lost in seconds. The crew's training emphasizes muscle memory, donning oxygen masks, initiating an emergency descent, maintaining control. But training assumes an intact airframe. When the structure itself is compromised, procedures collide with reality. Checklists become aspirational rather than prescriptive. Time compresses. Decisions that normally unfold over minutes must be made in seconds. The aircraft may still be flyable, or it may be in the process of tearing itself apart. Structural failures driven by pressurization do not always result in immediate loss of the aircraft, but they always redefine the margins. In some cases, the damage arrests after initial rupture, leaving the crew with a wounded machine that can be guided to a forced landing. In others, the failure cascades, with secondary fractures propagating as aerodynamic and inertial loads redistribute unpredictably. From a structural standpoint, the catastrophe is not confined to the initial crack. The rapid redistribution of loads places adjacent components under stresses they were never designed to bear. Frames that were once lightly loaded now carry concentrated forces. Stringers buckle. Tier straps, if present, may arrest crack growth, but only if the failure geometry aligns with their intended function. If not, the structure continues to unzip, guided by the weakest path available. The aircraft becomes a dynamic experiment in fracture mechanics, unfolding in real time at hundreds of miles per hour. The violence of this sequence exposes a fundamental vulnerability of pressurized flight. The fuselage is both a structural member and a life support boundary. When it fails, mechanical integrity and human survivability are threatened simultaneously. There is no graceful degradation. The system transitions abruptly from nominal operation to existential crisis. The design margins that once seemed generous are consumed instantly by the nonlinear nature of fracture. For investigators and engineers, the aftermath of such a failure is a stark demonstration of how little separates success from disaster. The crack that triggered the event may have been invisible to the naked eye only hours or days before. The aircraft may have completed thousands of safe flights with the same defect growing quietly in its skin. This reality challenges intuitive notions of safety, which often equate reliability with robustness. In pressurized structures, reliability can coexist with fragility right up until the moment of failure. The catastrophic sequence of a pressurization failure is not chaotic in the scientific sense. It is deterministic, governed by material properties, geometry, and physical law. What appears chaotic to human observers is simply the rapid unfolding of processes that were set in motion long before. The drama lies in the speed with which the system moves from equilibrium to destruction, leaving no opportunity for intervention once critical thresholds are crossed. This is the climax of the pressurization story, a moment when the hidden compromises of design, material choice, and operational assumption are exposed under extreme conditions. The aircraft does not betray its crew or passengers. It behaves exactly as physics dictates. The betrayal, if it can be called that, lies in the belief that such failures were improbable, that conservative design and careful operation were sufficient shields against the relentless arithmetic of fatigue. In the instant of decompression, that belief is stripped away, replaced by the raw reality of a structure pushed beyond its true limits. The immediate aftermath of a pressurization failure is defined by imbalance. The aircraft that emerges from the catastrophic sequence is no longer operating within the conditions for which it was designed, certified, or trained. Structural integrity has been compromised, aerodynamic assumptions are invalidated, and human performance is degraded simultaneously. Whether the event culminates in a survivable emergency or a fatal accident depends less on intent and more on how much of the original structure remains capable of carrying load. In cases where the aircraft remains airborne, the damage reveals itself brutally. The fuselage skin may be peeled back, exposing frames and stringers like the ribs of a broken organism. Interior panels are torn away. Insulation is scattered into the airstream. The cabin is no longer a controlled environment, but an extension of the outside atmosphere. Survivors describe overwhelming noise, extreme cold, and violent airflow that makes movement nearly impossible. The aircraft's pressurization system, designed to regulate pressure gently, is now irrelevant. The pressure vessel has ceased to exist. The crew's first objective is survival, not procedure. Oxygen masks provide the only barrier against hypoxia, but even with oxygen, cognitive function is impaired by stress, noise, and the sudden loss of situational certainty. Emergency descents are initiated instinctively, trading altitude for breathable air. But descent rates are constrained by structural damage. High-speed dives can exacerbate cracking, induce flutter in weakened skin panels, or overload damaged frames. The crew must balance urgency against restraint, navigating a narrow corridor between suffocation and structural collapse. If the aircraft manages to reach lower altitude, the focus shifts to controllability. Pressurization failures often coincide with secondary system damage. Wiring looms may be severed. Hydraulic lines may leak or fail entirely. Control inputs may feel heavy, delayed, or asymmetric. Flight control loss, an aircraft equipped with augmentation systems, may degrade or disengage as sensors deliver conflicting data. What remains is the raw mechanical relationship between pilot and machine, filtered through damage that no simulator can fully replicate. In accidents where the structure fails completely, the aftermath is defined by debris distribution rather than flight dynamics. Investigators analyze wreckage patterns to understand the sequence of breakup. Pressurization failures leave distinct signatures. Skin panels recovered far from the main impact site indicate in-flight separation. Deformed frames reveal whether failure was driven outward by internal pressure or inward by aerodynamic loads after rupture. The orientation of torn rivet holes, the direction of metal curling, and the presence of fatigue striations all contribute to reconstructing the final seconds. 4 fleets grounded after the discovery of a pressurization-related structural defect. The impact is immediate and far-reaching. Aircraft are removed from service, sometimes worldwide, pending inspection. Airlines face operational paralysis as schedules collapse and capacity evaporates. Maintenance facilities become triage centers, tasked with inspecting aging fuselages under intense scrutiny. Engineers revisit assumptions that were once considered settled. Inspection programs expand overnight, consuming resources and revealing additional defects that had gone undetected. Confidence in the fleet erodes rapidly, not because every aircraft is unsafe, but because the margin of ignorance has been exposed. The human cost extends beyond those directly involved in the event. Crews question the reliability of the machines they fly. Passengers confront the uncomfortable reality that safety is probabilistic, not absolute. Manufacturers face reputational damage that can persist for decades. Regulators are forced to confront whether certification standards were adequate or whether warning signs were missed. The aftermath becomes a systemic reckoning, not a localized incident. From an engineering standpoint, the immediate consequences force a reevaluation of what constitutes acceptable risk. Pressurization failures demonstrate that structural adequacy cannot be assessed solely through static analysis or short-term testing. The true test of a design is time. Fatigue does not respect optimism or precedent. A fleet that has operated safely for years can, under the right conditions, reveal a latent vulnerability with devastating effect. This realization reshapes priorities, elevating long-term durability to the same level of importance as initial strength. In hangars and laboratories, damaged fuselage sections are examined not as anomalies, but as evidence. Each fracture surface becomes a narrative of stress, environment, and time. Investigators search for patterns across multiple aircraft, correlating crack locations, growth rates, and service histories. Often, The aftermath reveals that the failure was not unique, but representative. Other aircraft in the fleet may be carrying similar cracks, poised at different stages along the same path to failure. Grounding the fleet is not a precaution. It is an acknowledgement that the system has entered a state of unacceptable uncertainty. The operational aftermath also exposes the limits of maintenance philosophy. Inspection intervals that once seemed conservative are revealed as insufficient. Visual inspections give way to mandatory non-destructive testing. Access panels are added where none existed before. Components once assumed to be benign are reclassified as critical. Maintenance manuals are rewritten, expanding in size and complexity as new inspection tasks are added. What was once routine becomes forensic by necessity. The pressurization failure, whether it ends in survival or loss, leaves behind a permanent scar on the industry. It disrupts schedules, careers, and confidence. More importantly, it disrupts assumptions. The idea that a structure can be trusted simply because it has not yet failed is dismantled. In its place emerges a more cautious understanding that every pressurized aircraft is engaged in a continuous experiment, one cycle at a time, with physics as the final arbiter. This immediate aftermath is not the end of the story. It is the point at which consequences become unavoidable and learning becomes compulsory. The machine has spoken through failure, and the industry must now listen, dissect, and respond. What follows is not just repair, but transformation, driven by the recognition that the cost of ignoring invisible degradation is measured not only in metal and money, but in lives.